Here with me, I've drawn a funny diagram of an atom, and I've color-coded the electron, proton, and the neutron. So the pink is for the electron, the blue is for the neutron, and this color, which I don't know the name, is for the proton. Right. So, and what I want to depict here is that the stability of an atomic nuclei. So this is a nucleus. Sorry, a nuclei rather. This is a nuclei, singular. So the stability of an atomic nuclei, that is how stable this nucleus will be, or nuclei will be, depends on the ratio of the number of proton to that of number of neutron, or the ratio of number of neutron to that of proton. So stability of an atomic nuclei depends on what the proton-neutron number or the neutron-proton number. Of course, it is a ratio. So for an atom whose proton-neutron number or neutron-proton number equal to 1 or closer to 1, that atom is said to be stable. So the atom is said to be stable. So it mustn't be 1. It might just be closer to 1. Let's say 0.9. So if you have an atom whose proton-neutron number is 0.9, that atom is stable. Or 0.89, that atom is also stable. 1.09, the atom will also be stable. But when you start having proton-neutron number, I've run out of space, a proton-neutron number of let's say 1.5, then the atom becomes a bit unstable, right? So the proton to neutron number ratio determines whether an atom will be stable or not. All right, so let's clean this up a bit and see, and try to see what this proton neutron number ratio is. Okay, now let's assume we have a proton, an atom with 10 numbers of proton, and the neutron number is let's say 12. Now, if you look at the proton neutron ratio, or the neutron proton ratio, that would be 12 over 10. So we will have 1.2, and this atom is going to be unstable. Oh, that's a bad spelling there. Unstable. Okay, unstable. So this atom is going to be unstable because it has a proton neutron number ratio that is greater than 1, right? So this atom is going to be unstable, and for such atom, it's going to undergo some kind of disintegration. So it's going to split for it to attain a stable state, right? So if we have, for example, let's say if now this from this diagram that I've drawn. So if you should count the number of proton, of course I have color-coded the number of proton to be blue. So if you should count the number of proton, we have 1, 2, 3, 4, 5, 6. So we have six number of neutron rather. Sorry. Then the number of proton is this color, right? So we have 1, 2, 3, 4, 5, 6. So we have 6. So the proton neutron ratio here is 1. So this is a stable atom, right? This is a stable atom. Now let's try to introduce more proton and see. Let me clean this up. So initially this has what? Proton number of 6, and neutron number of 6. So let's introduce more neutron proton and see how it affects its stability. Yeah, so let's put one more proton. That means we now have 7 proton and 6 neutron. So the proton neutron ratio will now be, so we have 7 over 6. Let me get out the calculator. Okay, 7 divided by 6. We have 1.16. All right, so we have 1.16, and that is approximately 1.2. So introducing more neutron makes this thing become what? Unstable. So for such atom as this is going to undergo disintegration, that is splitting of this nucleus. So this nucleus is going to split and the atom is going to divide. All right, so let's depict that. So we're going to assume some things here. So this atom is going to divide, so it's going to split into 2, right? So one is going to go this way, one is going to go this way. So let's draw a new atom now. 2 new atoms. So and we're let's assume that one of these proton was lost in that process. Let us put that here. It was lost in that process. Then that means we have 1, 2, 3. Since it is splitting, we have 3 protons here. Of course, our neutron is still 6 here, so it's going to be 3 here again. Now sometimes when they are splitting, it mustn't be the masses of the 2 daughter nuclei, which is what it is called in radioactivity. So the 2 daughter nuclei might have almost equal weight. So we now have 1, 2, 3 neutron, and this is the nucleus, right? This is the nucleus of one of the atom which splitted from this. And let's draw another this thing here. 1, 2, 3. Then 1, 2, 3. All right. So this is one nucleus, and this is the other nucleus. So one in the process of splitting, one of the proton was lost. Now, if we try to get the proton neutron number ratio here, proton neutron number ratio, we have 3 protons over 3 neutrons, so we have 1. That equal sign is funny. Yeah, 1. Okay, so actually that is stable since you have proton to neutron number ratio to be 1. Then that atom is said to be stable now. So let's look at this one. Of course, it's going to be the same, right? We have 3 proton, 3 neutrons, so we have 1, right? So the atom now splitting into 2 give birth to stable nuclei. So in the process, and a proton was lost, right? A proton was lost in the process, right? So this is the idea. This is actually the idea about radioactivity. Right? This is actually the idea about what? Radioactivity. So radioactivity is the spontaneous disintegration. Radioactivity is the spontaneous disintegration integration right, is the spontaneous disintegration of an unstable atomic nuclei with the emission of alpha particles, beta particles. I'm going to tell you what a beta particle is in a minute. Beta particles and gamma particles. That J is somewhat funny too. It's funny. Okay, so and also the release of energy. So radioactivity is the spontaneous disintegration of an unstable nuclei. So the nucleus must be unstable. So, and in the process, alpha particles might be emitted, and beta also might be emitted, or gamma might be emitted, and also energy is also released in the process. Huge amount of energy, right? So alpha particles are actually helium nuclei. This is helium, so it's also it's actually helium nuclei. So it is denoted with this letter alpha. So beta particles is actually electron with a 0 mass and -1 charge. All right. So beta particles are actually denoted with the letter. It looks somewhat like B, but it has this long tail, right? So gamma particle is actually fast-moving electromagnetic radiation. So it is denoted with this letter. It looks like Y, right? Okay. So now every element has its own decay constant and half-life. So I'm going to explain to you what that actually means, what an half-life or a decay constant actually is. All right, so let me clean this up. Hope I'm not boring you. Okay, so these notes, so take notes. This disintegration is actually a random process, right? It's a random process. It takes place randomly. It's a random process that is independent. That is independent of chemical combinations. So it is independent of chemical combinations, also independent of temperature and pressure. All right, so it is a random process and it is independent of chemical combination, temperature and pressure. So these things can actually affect how an unstable nuclei will disintegrate. So no physical factor will actually affect the way it will disintegrate. So take note of that. And it occurs when this disintegration occurs when an unstable nucleus, usually with atomic numbers that are greater than 83. So if you have atomic numbers that are greater than 83, like atom with atomic numbers that are greater than 83, then you start having unstable nuclei, and that is actually as a result of the proton number ratio being far greater than 1. Okay, all right. So the atom will now undergo natural decay in order to get, so the unstable nuclei will now undergo decay in order to give two different atoms that are stable. All right, so these two atoms that emerged from this unstable nuclei is actually called the daughter nuclei or daughter nucleus, depends on the number. All right, so let's look at the graph. Let's look at the graph. Let me clean this up. Let me look at the graph now. Okay, so let's say we have a graph. Okay, and on this axis we put time in seconds, and on this axis we put and the amount of the atom that remains. So let's use n for the amount of atoms. So it could be in terms of kilograms, number of atoms. All right, so it is actually found out that the graph is going to look something like this. Okay, so at time equal to 0, you might start with some amount of atom, which might be here. So let's call it original, the original amount of atom, which is n lowercase 1. So you will start with n1. So the time at that point might be is 0, right? Is 0. Okay, so or rather let's join this to this point here. Let's bring it down. No, of course it's not. Sorry, it's not going to be 0. Let me clean this up. It's not going to be 0. Let's call this one T1. So you started at time equal to T1 when the number of atom is N1. So you waited for some time so that the atom will undergo disintegration. And let's say you waited for some time. Let's say it is T2. So you waited such that the atoms disintegrated to half its initial. And you did this couple of times. I might not draw this to scale, but just try to get the feel of what I'm trying to depict here. So, and you waited for some time again, and this number of atoms reduced to half of this one again. So we have half of one, n1 over 2. That would be n1 over 4, right? So each time you now note this is the original amount that you put in. So each time you are conducting this experiment, you wait for the atom to go down half its initial amount, such that you have a particular time associated with that. So now the gap in between T1 and T2, I mean T2 minus T1, is actually called the half-life of the radioactive material. So it is same thing so it's going to be the same number for T3 minus T2. So it is irrespective of which one you take. So you could take T2 minus T1, or T3 minus T2, it will still give you the same half-life. So the half-life of a radioactive material is the time. Sorry for that message. Is the time it took. So is the time it takes for the radioactive material to reduce to half its initial amount, right? Half its initial amount. So note that T2 minus T1 is going to be a constant, which is the what? Half-life for each what? Radioactive material. So every radioactive material has its own half-life. So half-life is unique for every radioactive material. All right. Okay. So let me clean this up. Let me go to the next place, next page rather. Let me clean this up a bit. So we're going to be looking at formulas that will enable us to quantify what is actually happening in the process. Okay. This page is actually messy. All right. Okay. Let's go now. So let's look at some important formulas. Important equation that will enable us solve some radioactivity problems. All right. So the first equation we're going to look at is this equation is that is the half-life is equal to time over the logarithm to base 2 of r, right? So this is the half-life. This is the time it takes. You see, it could be now it might be the same as the half-life, greater than the half-life, or lesser than the half-life. So this is just time, and this is the half-life. Now r is called the disintegration ratio. Disintegration ratio. Note that this letter r is not a new quantity in physics. It is just something that we use to denote something that we use to make our work easier. So r is actually the ratio of the initial amount of the radioactive material to the final amount of the radioactive material. All right, so take note of that. Okay, and this is also equal to 2 to the power of n, where n is the number of half-lives. N is the number of what? Half-lives. Number of half-lives. So take note of this equation. So we could still write this equation as T equal to big T equal to small t over logarithm of 2. What is r? R is just n1 over n2. All right, n1 over n2. Okay, so let's look for another alternative way to this equation again. Since we know that r is equal to 2 to the n, we could still write that t is equal to big T is equal to small t over logarithm to base 2 of r. What is r? R is actually 2 to the nth power. 2 to the nth power, and this will be equal to now logarithm of 2 to the n base 2 is actually n. So we have t over n. So half-life, we could also write the half-life formula, which is big T equal to small t over n, right? Where n is the number of half-lives. All right, so take note of this equation. Okay, let me clean this up. So the second equation now is second equation is the number of radioactive element that decayed at some at a particular time interval is equal to the initial amount of atom or radioactive material minus the final amount. So this gives us the number of atoms that decayed, or the number of, or the amount of material that decayed for a given amount of time. So this is the amount of radioactive material that decayed, amount that decayed for a given amount of time. Okay, so the third equation is the fraction that is remaining. Fraction that is remaining. So the fraction that is remaining will be the amount that is remaining divided by the initial amount. So the amount that is remaining, which is N2, divided by the initial amount, which we started with, which is N1. All right, so take note of this. Now, but note that we said R, which is the disintegration ratio, initially we said that it is equal to what? N1 over N2. Now, look at this formula and look at this formula. It looks as if it is similar, but it is actually inverted. Because if you take N1 up and take N2 down, it will look like this. So we can say that this is actually the inverse of R. All right, so take note of this formula. Then, the fourth formula will be the fraction that decayed is equal to, now the fraction that decayed will be the amount that decayed over the amount that is remaining. So we have N that decayed over N remaining, right? Okay, so you take note of this formula. Now in the next video, we're going to be exploring examples, and we're going to be solving examples on using these formulas.